Okay, so today I'm going to do the first practice problem for homework number 8. This is involving internal flow. Okay, so let's begin by restating the problem. All right, we have a pipe, and flowing through that pipe is a liquid. Oops. And that liquid has a mass flow rate of 0.02 kilograms per second, and it has a diameter of 50 millimeters, which is 5 meters. I'm just going to go ahead and say what that radius would be, which is 0.025 meters. Okay, and we know that the fluid, which I believe is water, is at 27 degrees Celsius, which comes out to 300 Kelvin. Okay, so we know since it's water and we know the temperature, we're going to look up a few properties in table A.4. The first one we'll look up is the density, which is 998 kilograms per meters cubed. And we're also going to look up the viscosity, which is 855 times 10 to the negative 6th with units of Newton seconds per meter squared. Okay, so that's our restated problem. Next, we will do our energy balance / control volume step. We always do. And for that, I'm just going to draw a control volume around our pipe, because we're looking at the pipe in total. Oh, I forgot to tell you what we're even looking for. So the two things we're asked to find in this problem are A, the maximum velocity in the x direction we will experience in the pipe, and B, what is the change in pressure with respect to x. So our approach is, in general, any flow problem, we always just compute the Reynolds number. It's good to know if it's laminar or turbulent, etc. And the reason is because we're going to have to use the velocity profile, which we always write as u, being the x velocity, in order to solve for what the maximum velocity is. So to solve for u max. Okay? And once we also know u, we can find u mean, and we're going to use the u mean equation to find our pressure gradient. I'm working this problem from the perspective of I haven't worked it before. I've written the approach the way I think I should do it. We'll find I actually need to take a slightly different approach as we do the problem. Okay, so my analysis. First, the Reynolds number. So you remember you can compute the Reynolds number as a function either of mean velocity or mass flow rate. And we have mass flow rate right here. So we're going to use the mass flow rate form, which is 4 times m dot divided by pi d dynamic viscosity. When you plug in all of our values that we have, we get 595.6. So that is definitely laminar. Okay, so we know it's laminar, which means we can write the laminar velocity profile, which we could use to find the velocity at any point in our pipe. So if this is our pipe, and if we have a dimension r, which starts at the center line of our pipe, then we can write an equation, which we learned in class, and this is from the book as well, that tells us the velocity in the x direction at any point r. And this is what that equation looks like. The reason we had to find the Reynolds number is because this only applies for laminar flow, which we know we have. Okay, but we have a big problem, right? We don't actually know dp dx. That's something we're supposed to find, apparently, in part B. So what are we supposed to do here? How are we supposed to find this without knowing dp dx? I'm going to depart, actually, from the published solution to this problem and do something a little different. I'm going to solve for dp dx first, and then come back to this problem. There are smaller secondary equations in the book you could use that turn this first term into something else. But we're going to use this problem as an opportunity to discover what that would be. Okay, so you'll recall we have an equation for the mean velocity, which is mean velocity equals the radius squared, negative, divided by 8 times the viscosity times the pressure gradient. Okay, well, we don't know the pressure gradient still, but if we could find this, we know our radius and we know our viscosity. So do we know any more equations that have mean temperature in them? Well, we know one more. The Reynolds number could be computed as a function of the mean temperature. So since we already know the Reynolds number, which we found to be 595.6, then we can actually use the Reynolds number to find our mean velocity. So we're going to come over here. All right, so our mean velocity rewriting would be the Reynolds number times the viscosity divided by density times the diameter. And we know all of our values for there. We know the Reynolds number. We looked up viscosity, density. We know the diameter. So we can solve for our mean velocity, which is 0.01 meters per second. Again, the mean velocity is the average velocity of the flow inside of our pipe. Okay, so now we go back to our equation we were looking at before, and we rearrange it. dp dx equals minus um 8 times viscosity over r naught squared. And just so we're clear, what that is coming from this equation right here. We've rearranged it to get dp dx by itself. Okay, so let's go back down. So we have dp dx is equal to this, and now we can plug in the values that we have, and we get 0.109. And now we have to look at units. So we're going to do a little unit balance here. UM would be meters per second. 8 is a value, just a number. Viscosity has newtons seconds per meter squared. And in the bottom, we have meters squared. So when we write this out, our seconds cancel. And we have Newton meters on the top per meter to the fourth. Right? So we can cancel out one more meter and get newtons per meter squared times a meter. And a newton per meter squared would be a Pascal divided by meters, which is what we'd expect for a dp dx, change in pascals with respect to a distance x. Okay, so now going back up here, we plugged that in and we got a value for dp dx with units of pascals per meter. So that was part B, actually, what we just solved. Let's now do part A, which is what is U max? Okay, first we have to identify where does U max even occur. So going back to our equation for velocity up here, right here, we see that this all being a constant and r being our variable, which is squared, we actually have a parabolic velocity profile, which we said in class was true. For laminar flow, we have a parabolic velocity profile, where the maximum then would be at the center line, or r equals 0. So if we plug in r equals 0 to our velocity equation, we will find what the max velocity is. So u of r now with r equals 0, evaluated at r equals 0, just gives us 1 over 4 times the viscosity times dp dx times r naught squared. Now, something really interesting I just want to point out here. You'll notice that this actually looks kind of familiar because our mean velocity equation, remember, was minus r naught squared over 8 times viscosity times dp dx. So see, these terms all grouped are very similar, only changing by a factor of 2, right? So this is equal to this equation multiplied by 2. So this is an interesting conclusion. For laminar flow, our max velocity, sorry, that's not max, that would be mean, is just equal to double the mean velocity. That's true for any laminar flow. So plugging in our specific numbers, we get 0.0, is it 2? Yes, 2 meters per second. Okay, that's the problem. Thank you for watching.